Hello everyone. So welcome to the lecture today. You are already familiar with this course, right? It's Robotics Basics and Selected Advanced Concepts. Sorry for the delay. My mic was not working. But okay, so just a brief introduction about myself. I'm Soumya and I am a PhD student here at IIT Gandhinagar. So let's start with today's lecture. I hope I'm clearly audible and everything is clear because my mic was not working. I hope it is sorted. If someone could give me a heads up that everything is working fine and screen is shared.
All is perfect.
Okay, thank you. Okay, so yeah, so last time as we had seen, we looked into parallel manipulators, right? So last 2 weeks we were just discussing about parallel robots. We saw the basic loop closure equations. We saw what are the direct kinematics of parallel manipulators, what are the inverse kinematics for the same, and then we also came to know what is what platform manipulators, right? For that we saw direct kinematics and all of that. We also saw parallel of mobility of parallel manipulators, and then we saw a couple of examples. So there were a couple of examples last time from ISC Bangalore research. So we saw there was a sun tracking robot using 3DOF parallel manipulator, and then we also saw a Stewart Go platform for force torque sensor, right? And then there was something related to vibration isolation that we need to have for Stewart Go platform. So we saw all of these things, and from this I hope you are much familiar with parallel robots now. Parallel robots should not be a you have seen already that how inverse kinematics is easier in case of parallel robots, and then it is tough in case of serial robots, right? Because you might have multiple solutions coming up when you're trying to solve inverse kinematics problem for serial robots. So anyway, so I hope all of those things are clear and you're already familiar with the things. I hope you've gone through the lecture for this week, and it was based on velocity and static analysis of manipulators. So it introduces you to Jacobian, right? For serial and parallel manipulators both. And then you might have seen singularity. So in the very first lecture, I think I had discussed singularity, and it was an overview, but I hope going through the lecture would give you much more sense that what singularity is, and it can be best understood with the example of 2R manipulator, right? So I think you have understood that. We'll have some questions here and then we'll take that also. And then there are statics of serial and parallel manipulators. So all of these are the things that are covered in the last week lecture by Professor Ashita Ghoshal, and I hope all the things are clear to you. So let's start with a brief recap, and then we have some questions that we'll deal with and solve them, so that would help you in solving your assignments as well. Okay, so let's go with recap. Just let me just let me check if it is being recorded. Okay, fine. So yeah, so, in the very beginning of the lecture, I think you understood what velocity kinematics is. So, in the previous lecture, we had studied, in the previous couple of lectures, not exactly in the previous lecture, but we saw what is called the position of end effector, and what is the orientation of end effector, and what is meant by forward kinematics, right? And what is the workspace that this robot covers? So we saw all of those things. So all of those things, position, orientation, forward kinematics, and workspace, all of these these things answer the question, where is the robot? Okay, just related to position. Yagnesh, thank you. Okay, now what we want to ask is how fast the robot is moving. So that is velocity kinematics. So we want to answer the question now, how fast the robot is moving, and that you already understand by velocity kinematics, right? So we are starting with velocity kinematics today. Okay, so velocity analysis, why is it required? Why do we even need velocity analysis? Any answer to this question? There could be couple of points. Why do we even care about the velocity? And what do we want to find out? First thing, let's talk about what we want to find. Okay, so it could be linear velocity of a point on a robot. It could also be end effector, but I am denoting it by general point, so that let's say we want to find the position of a single link, how do we go about it? Or it could be angular velocity of some rigid body. Okay, and maybe we want to find out relationship between joint rates. What is joint rate? So you know that these angles are thetas. So theta dot is the joint rate. So we want to find out the relationship between joint rates and end effector velocity. Uh, that means when this theta is changing, it is changing at some rate, right? Theta 1, theta 2. How do the rates affect the velocity of this end effector? Right. So if there is some concern about this, we definitely have to go for velocity analysis. So velocity analysis is required because so later we'll see wheeled mobile robots and manipulators. You have already seen the serial ones, right? So it is required for motion control. It is required for tracking of some path or some force analysis. Let's say this end effector is supposed to apply what amount of force, or if you want to do singularity detection, singularity we'll discuss later as well. But just for now, if you want to do singularity detection, so for all of these things, this velocity analysis becomes essential. Okay, so so let's start from linear velocity of a rigid body. Okay, so it is absolute basic. So let point OI, okay, be fixed in the rigid body. So what would be the position vector? It's sorry, its position vector in frame of origin, which we denote by 0, is position of the ith link with respect to the origin is a function of time. So we denote it by this. Okay. Uh, okay. So let's define linear velocity now. So I think I should not write it this way. I should write, okay. So everything that we'll be doing will be with respect to this OI, which would be fixed in that rigid body. Okay. So yes, Yagnesh, do you have any question? Okay, just a second. Uh, Ma'am, can you please share anything that could help in preparing for the exam at the end of the session? I searched online, also posted in discussion. Reply, and can you discuss how the question papers were in previous years, like what topics to focus more and all? I'm not aware of the question papers because it is never shared with us. So I'm not aware about that, but I'm pretty sure that going through the lecture completely, whatever professor is teaching, and going through all the assignment questions would be sufficient. So the questions that I am taking up here in the session are more of si- are similar to that of assignment. So if you're solving the assignment, you might have seen the questions that I'm taking here are very similar to them, and it just helps you in uh, conceptualizing the concepts that are taught in the lecture by professor even more. So I think these three things are sufficient. Don't go beyond. If you want to go beyond, go for Professor Ashitava Ghoshal's book. Okay? You can go with it. Just let me check the name of the book. I'm sharing it right away. Uh, where would I find it? It should be in announcements. It should be in about the course. And I think the book was referred here. Just let me check. Mm, yeah. I think something is wrong with my laptop. Not able to figure out. Just hold on. Something went wrong. Now I think it is fine. Yeah. So this book is by Professor Ashitava Ghoshal himself. So just have a look at this book. Okay. And there was some other question. 60% at most the assignment 60% are a common exam and the MCQs. I did not understand what you are saying, Shravan. Assignment is 60%, that is what you are saying. And MCQ is more dependent on the course. Okay. So all in all, what I have got to say is my screen is flickering. I think I'm having some issues with my laptop right now, but still I'll carry on till the time I can. So yeah, the thing is, when you study for exam, study the complete lecture by professor, and then solve all the assignment questions. You can also go through this book. Okay. And once you go through this book, that should be sufficient. Okay. Okay. So let's move forward. So how do we define linear velocity? So linear velocity of point OI with respect to frame 0 is 0 VOI is equal to d of d differentiate the positions, right? So it would be ROIT. Okay, after this we can just expand it, and how it can be expanded. VOI is limit delta t tends to 0, and it will be, so whatever is coming here that would be inside the limit. Okay, so we'll write it for t and t plus delta t. So it would be, it's just very basic, it t plus delta t minus ROI 0 t upon delta t. Right, this is just straightforward differentiation, nothing very new in this. So when we differentiate, the differentiation is done in frame 0, right? Okay, so just two coordinate systems are involved here. One is frame where derivative is taken, and second is frame where velocity is expressed. Okay, so if velocity is computed in frame 0, but what do we want? We want velocity in frame I, because we want the velocity of the length, right? Let's say in frame J, if we want it, so it would be J 0 VOI is equal to J 0 R 0 VOI. So velocity transformation is via a rotation matrix. This should be very clear. Okay, so differentiation frame and description frame are different concepts. The differentiation is done in frame of origin, which is 0, and the resulting vector can be expressed in any frame. If we want to express it in frame J, then we have to multiply it with a rotation matrix, right? Now let's talk about angular velocity of a rigid body. Okay, so a very important question that we have here is, can we differentiate Euler angles? What are Euler angles? Directly to get angular velocity? If you have seen the lecture, you would get the answer. So the Euler angles are, let's say, phi, theta and psi, the three different angles which are used to express the orientation. So my question is, if we differentiate this and this, would we get omega x, omega y and omega z? Would that happen? Am I audible? Can someone answer it? And please don't answer in the chat box, because the tab screen is shared on my screen and I'm not able to switch on that. Moreover, I'm facing some problem with my laptop and I'm not able to switch between the screens. So if you can speak, that would be helpful. So it's a very basic question. If I differentiate the higher angles, would I be able to get the angular velocity? Okay. Can we define angular velocity? Let's not confuse by the notations, as phi dot, theta dot, and psi dot. Is this sufficient to let us know what is the angular velocity of the body? I hope you know the answer. The answer to this question is clearly no. And why it is no? The reason it is no is that Euler angles are not Cartesian quantities, are not independent Cartesian quantities. Okay. So their time derivatives do not directly give physical angular velocity. Okay. Instead, we derive angular velocity from rotation matrix. How do we derive it? It is from rotation matrix. All right. Okay. So from here, let's start. Derivation of angular velocity from rotation matrix. Okay. So let rotation matrix from some frame link frame I to the origin frame B Ri 0. Okay. It is with respect to the ith frame. So what is the property of rotation matrix? You know that R transpose is equal to identity matrix, and this is orthogonality. Okay. So let's differentiate this. Differentiate both of the sides for this. It would be R dot. So let's take the first term, differentiate it, keep the second term as it is, plus R dot transpose. Okay, is equal to 0. Let's rearrange it. Take the transpose of the first term. It would be R dot R transpose cut transpose. Okay, it would be R dot transpose. Okay, after this the equation eventually becomes R dot R transpose plus R dot R transpose cut transpose is equal to 0. What does this mean? And can we deduce anything from here? If a matrix is written such that A plus A transpose is equal to 0, what does this mean? No one knows the answer? I won't be able to see the chat box, so please unmute yourself to answer. This is very basic, come on. If a matrix is written such that A is equal to minus A transpose, what does this mean? What can you say about this A matrix? Can you say something? Okay. What is a symmetric matrix and what is a skew symmetric matrix? Okay, since no one is answering, I'll take it forward. So from here, if this property is observed for the matrix, we can say from here that R dot R transpose is skew symmetric. Alright. So let's denote it by some quantity which is omega. So omega is a matrix which comprises of R dot R transpose. And how it is written? Since it is a skew symmetric matrix, we can write it in the following ways. Its diagonal elements would be 0, right? And here it would be minus omega x, omega y, minus omega z, omega z. Okay, so this corresponds to this complete thing corresponds to a vector which is omega is equal to omega x, omega y and omega z. Okay, and this is the angular velocity transpose, and this is the angular velocity of frame I with respect to 0. Okay, so why is this physical angular velocity? Why this is physically angular velocity? So let's say there is a point fixed in the body frame. Let me write the question first that we want to answer. So let point P be fixed in the body. So its position in fixed frame can be given as position with respect to 0 can be given as Ri into P. Okay, if we differentiate it, what would happen? You differentiate on the left hand side, you also differentiate on the right hand side, and so since P of ith length, which is the position, is RT into something the position in the 0 frame, right? It is just uh, the link is rotated just by multiplying with a rotation matrix. So if we substitute it here in this equation, what would happen? 0 pi would be r dot rt 0 p. Okay, and after this, from here we can write p dot 0 is equal to omega 0 p. But we know another thing, that a skew symmetric matrix acting on vector equals cross product. Okay, which means this omega into p would be equal to omega cross p. Okay, so from here what we can say is, therefore cross p, this is exact rigid body rotation velocity formula, and from here we can say that this omega is the angular velocity which comes from the skew symmetric matrix. Okay, okay, so let's move to this topic. I'm just revising what is taught and then we'll move to the question. Space fixed versus body fixed angular velocity. Okay, so there are two ways to define. Let's see this. We already saw that this omega is r dot r transpose. So this is angular velocity expressed in fixed frame. So for body fixed, we can start from r transpose. R would be equal to identity matrix. We differentiate it. Okay, so rt r dot transpose is equal to 0. We define omega L to be equal to RT R transpose. This is also skew symmetric. It corresponds to, this is also skew symmetric. Okay, and it corresponds to angular velocity expressed in body frame. Okay, so the relation that we have is the following: omega s is r times omega p. All right, we use space fixed angular velocity. Okay, then after this we can talk about velocity propagation in serial manipulator. Okay, now we will apply all of these ideas to robots. So let's talk about rotary joint. Okay, let's say link I is connected to link I minus 1, okay, by a revolute joint about z axis. Okay, so what would be the rotation matrix? Rotation matrix for the ith link would be rotation matrix of I minus 1 link into rotation about the z axis by angle theta I. Okay, so after this you might have seen we differentiate it and later we finally arrive at this thing. Omega I is omega I minus 1 plus z I hat theta I dot, right? This is really important, and from here we see that angular velocity accumulates. Okay, each revolute joint adds its rate about the fixed axis. Okay, Linear velocity propagation is relatively simple. We know that the position is Ri. Let's denote it by R. Ri is the previous position, which is Ri minus 1 plus Ri minus 1 into Di minus 1 into I. This is basically the distance between the two links, the length of the link, or the translation basically between the links. So and that translation cannot be used directly, right? We have to have a rotation matrix. So this is standard rigid body relation. So for velocity from here we'll get Vi is equal to Vi minus 1 plus omega I minus 1 cross Ri minus 1 into D. Okay, let's talk about prismatic joint. Okay, so for prismatic joint, omega I is equal to omega I minus 1, because we only have translation and no rotation. So the only thing that, so this would be true for angular velocity. Okay, and for linear velocity, Vi would be Vi minus 1 plus omega I minus 1 cross R plus di dot into z hat. So prismatic joint contributes only translational velocity. Okay, let's look at an example that was also taken there. So if we talk about planar 3R manipulator, and let's say the axis of rotation of all the revolute joints is about the z axis. Okay, and the link lengths are L1, L2 and L3, and the joint variables are theta 1, theta 2 and theta 3. If I hope you understand what is I shouldn't okay, let's say it has end effector here. So this angle, this is theta 1, this is theta 2 and this is theta 3. So you know very well how do we write the position of the end effector, right? X comma y. It is just sine and cosine of all these terms. So let's say omega 1, which is for link 1, is 0 theta 1 dot, right? Because it can only rotate about the z axis. But omega 2 is no x, no y, and theta 1 plus theta 2 dot. Okay, and omega 3 is 0 comma 0 comma theta 1 dot plus theta 2 dot plus theta 3 dot. Okay, and from end effector position, if you want to write what is x, what it would be, let's say the lengths are L1, L2 and L3. It would be L1 cos theta 1 plus L2 cos theta 1 plus theta 2 plus L3 cos theta 1 plus theta 2 plus theta 3, right? Y would be same quantities but in terms of sine. Okay, sine theta 1 plus theta 2 and L3 sine theta 1 plus theta 2 plus theta 3. Okay, we can differentiate this to get the velocity. So x1, sorry, x dot is equal to minus L1 sine theta 1, cos theta ka differentiation is minus sine theta, right, into theta 1 dot plus L2 sine theta 1 plus theta 2. So from here we'll have a minus sign coming, and the differentiation would be theta 1 dot plus theta 2 dot. Again we'll have a minus sign coming. I'm writing it before only. L3 sine theta 1 plus theta 2 plus theta 3 into theta 1 dot plus theta 2 dot plus theta 3 dot. Okay, similarly you can write y dot. I'm not writing it, it is very simple, it's just a differentiation. So this is complete velocity propagation, okay, in case of 3R manipulator. Okay, now important part. This is Jacobian. Okay. So Jacobian relates the linear velocities to the joint velocities. Okay, where V comprises of all the linear and angular. Yeah. So Jacobian is a metric that maps joint rates, all the joint rates to the end effector velocity. Okay. Matrix that maps all the joint rates theta 1, theta 2, theta 3, all of the dots, theta 1 dot, theta 2 dot, theta 3 dot to end effector velocity. What is the linear and angular velocity of the end effector? Okay. So there are few important points. Jacobian is configuration dependent. Okay. It is time varying and it is not dimensionally homogeneous. Okay. So you might have already seen that the top three rows are length and the bottom three rows are unitless. So condition number is physically meaningless unless normalized. Okay. So let's talk about a 2R manipulator. We know that V is equal to J theta dot. So if we take the magnitude, it would be theta dot transpose J theta dot. We can define G as J transpose J. So basically V square that we wrote here, right, it would be equal to theta dot T G theta dot. So we can constrain the joint speed because you do not have the liberty to go at any speed, and maybe you a standard way is to map them to a unit circle. Okay, you can find the minimum maximum velocity. I hope you are aware of Lagrange's multiplier by now. So from here G theta dot is equal to lambda theta dot. This is eigenvalue problem now. So the eigenvalues for this are lambda 1 and lambda 2. So the maximum velocity that you get is under root lambda 1 and the minimum velocity that you get is under root lambda 2. Okay, and then you might have already seen the velocity ellipse. That what was the concept there? The concept was velocity endpoint traces ellipse. Okay, the major axis is under root lambda 1 and the minor axis is under root lambda 2. So the physical meaning of this is, it was made very clear in the lecture that the robot moves more easily along major axis. Okay, if both of them are equal, lambda 1 is equal to lambda 2, that means that it is isotropic. The movement is similar in all the directions with no bias. Okay, so for 2R manipulator, G11 is equal to G22 in the G matrix. Okay, it eventually leads to L1 is equal to root 2 L2 and theta 2 is equal to 135 degree, and this is, and for this it is very special geometry is required to achieve this isotropy. All right. Then there are redundant manipulators. And if there, when a manipulator is called redundant, any answer? Does anyone know? When is a manipulator called redundant? If there are more joints than task dimension. So in that case, Jacobian matrix won't be square. Okay. So in that case, so you saw that we already used V is equal to J theta dot. Now if you have to find theta dot, what you would do? You would multiply both the sides by J inverse into V, right? For inverting this Jacobian matrix, this should be a square matrix, right? If it is a non-square matrix, what do we do? So in that case, in case of redundant manipulators, when the J matrix, Jacobian matrix is not a square matrix, we take pseudo inverse. Okay, and how is pseudo inverse taken? It is J transpose J transpose inverse. Okay, so the solution that you get from here is theta dot is J pseudo inverse into V plus identity matrix minus J pseudo inverse J into omega. This second term is in null space. Okay. Okay. All of this is used. Why this is important? Because we use it for avoiding obstacles, not reaching the joint limits, and maximizing the manipulability. Okay. Okay. So parallel robots, they have passive joints. We already saw this, right? Apart from all the actuated joints, they also have passive joints which are not actuated. For example, in 3-DOF RPS manipulator, only the prismatic joint is actuated, the revolute joint is not actuated, and it is an example of passive joint, right? So parallel robots have passive joints, and there is no natural velocity propagation. Okay, so we need constraint equations. Okay, and what are the constraint equations there? Let's say we denote it by eta of q is equal to 0. If we differentiate it, what do we get? I'm not going into much details that how it was discussed in the lecture, but it is k into theta dot plus k star into phi dot. This theta is for the actuated joints and this phi is for the passive joints, is equal to 0. You solve for phi dot, you get it to be minus k star ka inverse into k into theta dot. Okay. You substitute this into velocity equation. Okay. And define an equivalent Jacobian. Which is given by J minus J star K star inverse K. Okay, so the final thing is V is J equivalent into theta dot. It is not J as simple as it was in case of serial manipulators. Okay. After this, let's come to singularity. Okay. So what happens in case of singularity? If you look at it mathematically, determinant of J is equal to 0. This is the notion. When the Jacobian loses its rank, there arises a case of singularity. Now, singularity, let's understand with the help of an example. Let's say, okay, I think all of you can do one thing. If you stretch your arm completely, so your hand is a 2-DOF manipulator, right? Sorry, 2R planar manipulator, right? So all it can do and just think that your shoulder joint is fixed and you have 2R manipulator with you, and then you stretch your arm completely. There shouldn't be any angle in between L1 and L2. Okay, and once it is completely stretched, if you want to move it, you can only move in the tangent direction and you lose the control in the direction of the hand. So let me explain this with the help of figure. Let's say this is your uh, fixed face, and from here let's say you have one link, two link, right? Let's say the length is L1, the length is L2. Okay, it's maintaining some angle here theta 1 and some angle is being maintained here which is theta 2. Okay, let's say the conditions change and my L1 is like this, but I have L2 completely like this. Okay, so there is an angle of either 0 degree or 180 degree. 180 degree is correct? No, 0 or 360 degree, 0 or 2 pi in between both the links. Okay, now the workspace that it was going to cover was this. Okay, now it is completely in a straight line, like both the links are completely in a straight line. Then what is going to happen? Would this end effector be able to move in this direction? No, right? It can only move along this tangent to the circle, either in this direction or this direction, but it cannot move in the direction of its length, which it was able to do when it was at this position. Then it was able to move in this direction as well, but now it is not able to move. It has lost 1 degree of freedom. Alright, it has lost 1 degree of freedom, and the Jacobian has essentially lost its rank, and hence we have lost a degree of freedom and we are not able to move in that direction, but we can move in the other direction. Now this is a very simple example and it can be clearly visualized, right? Because it is a 2R manipulator. What if there are more number of links? Is it easy to visualize? No, right? If there is a robot with let's say 5 links and 5 joints, would you be able to visualize this? No, because it won't happen only in this case of stretching. There are many cases for that robot in which this situation will occur. And how do we talk about that? How do we figure out if such case is happening? That can be figured out with the help of this. If the determinant of the Jacobian loses the the determinant becomes 0, or the rank of the matrix of the Jacobian matrix is lost, we say that we have arrived at the case of singularity. We have arrived at singularity condition. Okay, so the thing is, singularity is okay. Just hold on. So at singularity, some end effector velocities cannot be produced. Okay, you would see that for moving in this direction you will need to move with infinite velocity, which is not possible, and all of that cases will occur, that we'll see. But before that, some end effector velocities cannot be produced. Infinite joint velocities may also be required, right? And then robot loses instantaneous mobility and mechanical advantage is not there. So singularity is a property of configuration and it is not just a property of robot design. Okay, the configuration you are in actually decides if you are in singular configuration. It is a property of design of a robot, but not only design of the robot, because in this case you don't have singularity. It has something to do with design, but in this case you have. So it is because it is in this particular configuration. Okay, now if we talk about it geometrically, I think I'll change the color of the pen. Geometry meaning via velocity ellipse. Okay. So we know that we already saw this. V square is theta dot transpose j theta dot, where we said that this is G matrix. G or D transpose, what it was? I don't exactly. It was G. Okay. Okay. Yeah. To match a dimension, it should be G. Okay. So at singularity, what would happen? Lambda minimum, whatever would be 0. So basically velocity ellipse. So for this end effector you get an ellipse, but for this you just get a straight line. So velocity ellipse collapses into a line. So the robot cannot move in one direction, and that direction corresponds to null space of J. Okay. So if you want to derive it mathematically, I think we can do. So let's say for 2R planar manipulator, we are deriving it. Okay. So I'm okay. Let's draw it also. Let's say this is your theta 2. This is the end effector. This is theta 1. Okay. This is L1 and this is L2. So your end effector position, which is given by x comma y, is what? X is L1 cos theta 1 plus L2 cos theta 1 plus theta 2. Similarly, y is L1 sin theta 1 plus L2 sin theta 1 plus theta 2, right? If you compute the Jacobian, how would you do that? You would differentiate it first. So x dot is minus L1 sin theta 1, theta 1 dot minus L2 sin theta 1 plus theta 2 into theta 1 dot plus theta 2 dot, right? Your y dot would be L1 cos theta 1 dot plus L2 cos theta 1 plus theta 2 theta 1 dot plus theta 2 dot. If we rearrange it, what we would get as Jacobian in terms of theta 1 dot and theta 2 dot? Let's say we have theta 1 dot, theta 2 dot here. So how is the velocity related to both of them? We essentially want this, if it is not clear. Jacobian theta 1 dot, theta 2 dot. Okay, so this is the Jacobian that we want to find out. Okay, what it would be? Minus L1 sine theta 1 minus L2 sine theta 1 plus theta 2. Here it would be minus L2 sine theta 1 plus theta 2. Okay. Here it would be L1 cos theta 1 plus L2 cos theta 1 plus theta 2. And here it would be L2 cos theta 1 plus theta 2. Okay. So once we have this Jacobian matrix, so from here determinant of J would be, if you find the determinant of J after solving everything, it would be very simplified and would just be L1 L2 sine theta 2. Okay. So from here you can see the determinant of the Jacobian only depends on L1, L2 and theta 2. Now this L1 and L2 can never be 0 or anything, like it is a fixed quantity and it is a constant. But this theta 2, this angle actually has an effect. So if sine theta 2 would be 0, the determinant of J would be 0, which makes the configuration singular. For this, theta 2 has to be either 0 or pi. Sorry for saying 2 pi. 2 pi was same as 0. 0 and pi both. Okay. So either you have the hand like this, or sorry, completely extended, or you have it both in the same direction. So 0 or pi. Okay. So in both these configurations, so this is what we saw visualized as well, right? You cannot move in one direction. Similar thing that you can arrive if you compute the Jacobian and check the determinant, etc., and you'll see. So this corresponds to fully stretched arm or fully folded arm. Okay. At this configuration, the links are collinear, right? And the end effector cannot move in this radial direction, this direction. It cannot move. Why? Because both joints generate velocity perpendicular to the links. Okay. So radial motion is impossible and the velocity ellipse collapses to a straight line. So there are a number of singularities in serial manipulators. One is boundary singularities. Okay. When does it happen? It happens at workspace boundary. The one example that we saw. Example 2R is fully stretched. Okay. The second is internal singularities. Okay. It happens inside workspace. Okay. And a common example that I can give you, which you can look at, is wrist alignment in 6R robot. Okay. And the other is wrist singularity. So this is not a very different type, but still I am writing it because it can be taken from industrial robot example. So in 6R robot with spherical wrist, actually both of them are nearly same, but still we are writing it. Spherical wrist. So what happens if the wrist axis aligns? Jacobian loses the rank, and the robot loses one orientation degree of freedom, and it is very dangerous in case of industrial robots. So if rank of J is 1, right, in 2R case, which we already saw, only one independent velocity direction is possible, which is in this direction to the end effector. Null space dimension is 1. There exists one non-zero theta dot such that J theta dot is equal to 0. This means that internal motion without end effector motion is there. Okay. Now, okay. Uh, let's go to singularities in parallel manipulators. Okay. Let's talk about this. So parallel robots have two Jacobians from constraint. So we already saw J equivalent wala concept, right? K into theta dot plus K star into pi dot is equal to 0. So the equivalent Jacobian that we get here is J minus J star K star inverse K. So there are two types of singularities here. One is inverse kinematic singularity. Okay. So it is in this case it is just a determinant of J equivalent is equal to 0. It is similar to serial singularity, right? So the second is direct kinematic singularity. Here the determinant of K star becomes 0. This is important. This implies that the constraint matrix becomes singular. Robot loses stiffness. Platform can move even when actuators are locked. Okay, and yeah, so in many cases it would be dangerous. But yes, this is the example. So in the lecture there was another example taken which I won't discuss in much detail right now, but it was for planar 4 bar mechanism. Okay, so you can see that there are two constraint equations that are written there, and then we just differentiate it and arrive at this equation: k theta 1 dot plus k star phi dot is equal to 0, and then singularity happens when determinant of k star is equal to 0. So it happens geometrically when the links become collinear at that configuration, or mechanism gains extra mobility. Okay. Okay, after this there was something covered about statics of serial manipulators, right? So what happens in case of statics? The work done, net work done is 0. Okay, so if we talk about work done by joint torques or the motors, what it would be? Torque into delta theta. Work by external force would be F transpose into del X. If we equate it, okay, and then we substitute velocity, uh, okay, velocity relation. So since del X is equal to J into delta theta, so torque, we already know this. So from here, I'm not just doing all the calculations and everything. From here, you will know that torque is J transpose into F. Okay, which means external torque is mapped to, sorry, external I think I'm making some mistake. Just external wrench is mapped to joint torques. Okay. So if we take planar robot example, let's say to our manipulator example, manipulator force analysis. Okay. So let force at end effector Bf is Fx and Fy. Okay. And torque is J transpose F. So if you compute the torque's relation with the force, what you're going to get is L1 sine theta 1. I'll just use the shorthand. That's in sine theta 1 minus L2 sine theta 1 plus theta 2 into Fx plus L1 cos theta 1 plus L2 cos theta 1 plus theta 2 into Fy. So torque 2 would be minus L2 sine theta 1 plus theta 2 into Fx plus L2 cos theta 1 plus theta 2 into Fy. So if arm is stretched, theta 2 is equal to 0, then the torque required to resist radial force becomes infinite. This explains that at singularity, the robot is going to lose degrees of freedom. So the robot can resist some forces with 0 torques. Okay. Okay, so I think I've covered. So but there is similar to this velocity ellipse. We also have force ellipse, right? On which the measure axis, on the measure axis, it is easy to resist force, and on minor axis it is hard to resist force. So at singularity the force ellipse becomes unbounded. Okay. Uh, I'm not going into details of statics of parallel manipulator because in the interest of time we have to take the questions. But for parallel robot also there are internal constraint forces and they are even more complicated. So if there is a singularity in the direct kinematics, the robot loses the stiffness, cannot resist certain forces, and platform can move under zero actuator torque. So, okay. So the thing is, singularity is not merely mathematical, right? It represents loss of mobility. Okay, infinite joint velocity also happens, and then there is loss of stiffness in case of parallel robots, and it can lead to some dangerous configuration in real robots. So okay, so the Jacobian remains the same. It is just connected. It is just linked in a different way for the forces and torques and for velocities and joint rates. And okay, this duality is fundamental to robotics. Okay. After this, let's solve some questions. The linear, sorry for my handwriting. Yeah. The the linear velocity of the origin y of a coordinate system I with respect to I is always 0, need not be 0, is defined as this we already saw, right? This is just the same expression, t upon delta t, and then is not defined in coordinate system I. Okay. So this is a conceptual question and it basically checks if you understand the difference between differentiation frame and description frame and what is the velocity of origin, etc. And okay, whether moving of the whether the velocity of a point fixed in a moving frame is 0 or not. So let's go about it. So from here, if we understand the things correctly, we'll see what is this OI. This OI is the origin of moving frame I. Its position vector is expressed in fixed frame 0 as 0 ROIT. So this position changes with time if the frame is moving. Okay. Okay. By definition, we already know this. This gives velocity expressed in frame 0. We already saw this. So can it be expressed in frame I? Yes. To express the velocity in frame I, if we substitute everything, we get this. So this is correct. Okay. Is velocity always 0? Now you can think that the origin of frame I is fixed in frame I. So its velocity must be 0. That is the whole trap here. Okay, this is wrong. Why? Because velocity is defined with respect to another frame. We are computing velocity of OI with respect to the origin. Even though your this thing is equal to 0, this does not mean your velocity is equal to 0. If frame I is translating, its origin moves. This velocity need not be 0, and the option 1 is wrong. Okay, this is already correct. So need not be 0 is correct. Okay. So, and the other option was, is velocity not defined in coordinate system I? This is incorrect, right? Because velocity can always be expressed in any frame using the rotation matrix. There's no restriction. So option 4 is definitely wrong. Okay. So the final correct answers are need not be 0, and it is defined as this expression. So frame dependence of velocity is basically asked here, and what is the difference between differentiation and description, and you should have a proper understanding of the moving coordinate systems, right? Okay. The space fixed angular velocity vector of a rigid body is same as the time derivatives of three Euler angles used to describe the orientation of a rigid body in 3D space. It can be derived from the time derivative of a rotation matrix R. Okay. The other option is it can be extracted as a skew, it can be extracted from a skew symmetric matrix R dot transpose R. Okay. I don't know, the main question here is if that matrix you're writing it correct or not. That is a major question. So I'll just write from skew symmetric matrix. Can someone remind me what it was? What was this matrix? And where R dot and R are the, you already understand that, right? They are time derivatives of the rotation matrix and the rotation matrix of the rigid body in 3D space respectively. And in the other option we have the same option, but this thing is R dot R transpose. Okay. Okay. So let's see this. So we want to first know what is the difference between space fixed and body fixed angular velocity. That is the first thing. And then which skew symmetric matrix actually corresponds to which angular velocity. So, and you should have a conceptual understanding of why Euler angle derivatives are not angular velocities. Okay. Okay. So the space fixed angular velocity the space fixed angular velocity of a rigid body is same as time derivative of three angular angles is the correct answer. Is given in the first option. Do you think it is correct? We saw it just few minutes ago. So For getting the angular velocity, we do not go with the time derivatives of the Euler angles, but we know that all of them are dependent, and then we need to differentiate them. Differentiation of rotation matrix actually gives us these space fixed angular velocities. Okay, so if you differentiate it, the derivation that we did earlier, we came to know that this matrix r dot r transpose is actually a skew symmetric matrix which can be defined by omega, and this omega is a skew symmetric matrix with the diagonal elements as 0 0 0, and then we have omega x, omega y, and omega z. So the vector that we get from here is omega x, omega y, and omega z transpose, and this is a space fixed angular velocity vector. Okay, so this option is definitely correct. Okay, now uh, I think yeah, it can be derived from the time derivative of r. So let's go option by option. The first option, it is same as the derivatives of Euler angles, and this is wrong because Euler angle derivatives are not angular velocity components. So your gamma alpha dot and beta dot and gamma dot do not suffice. Okay, so it is not equal to them. Then the other option is it can be derived from the time derivatives of r. Yes, angular velocity so this is incomplete. The problem is this is incomplete. Angular velocity depends on r dot, but r dot alone is not skew symmetric. Okay, we must multiply it by r transpose as we saw here. Okay, so without r transpose you do not get angular velocity matrix. Thus this statement is imprecise and incomplete. That is only the reason we are ignoring it. The third is it can be extracted from a skew symmetric matrix, and the matrix is given by this. Okay. If you find it like it corresponds to body fixed angular velocity and not space fixed, if you look at the derivation. So yeah, the question asked was space fixed, so this won't work. And the fourth option is the exact derivation that we did. So one important conclusion that you have from here is r dot r transpose is space fixed, and r transpose r dot is body fixed. Okay, so angular velocity depends on where you multiply the derivative. Right multiplication is space fixed, left multiplication is body fixed, etc. So this is tensor transformation property. Okay, let's move to the third question. The space fixed angular velocity vector is independent of the choice of the orientation of the body coordinate system, is independent of the choice of the orientation of the fixed coordinate system, is dependent on the origin of fixed coordinate system. I'm not writing it, I'm writing CS, is dependent on the origin of body coordinate system. Okay, okay, so It basically is testing what space fixed angular velocity means, what changes if we redefine the body coordinate frame, and what angular velocity depends on geometrically. Okay, so what is the definition of space fixed angular velocity? We basically uh, arrive at this q symmetric matrix that we already saw, and then it describes how the rigid body moves in space, right? Suppose we change the body coordinate system. We attach a different coordinate frame, okay? I dash, let's say it is I dash, to the same rigid body. This new frame differs from I by a constant rotation, right? So it is just a constant rotation matrix. It does not depend on time. It is just one rotation different. So this means we reoriented the body coordinate axis, but the body itself is unchanged. So if you try to compute the angular velocity with the new frame, what would you get? You would get that changing the orientation of the body coordinate system does not change. Okay. So from there, so if you want to derive, you can derive it as well. Should I derive it, or you guys would derive it on yourself? I think I'll do it for you. Okay. So let's say we define omega r dot r transpose, okay, where r is rotation matrix to 0. So R maps body frame I to fixed frame 0. Okay. Now the angular velocity vector that is extracted from its skew matrix is omega I 0. This is the space fixed angular velocity vector. Okay. It describes how the rigid body rotates in the space. Okay. Now suppose that we change the body coordinate system. Okay. So we attach a different coordinate frame, which is I dash. So the new frame R dash differs the original frame by a rotation matrix. Okay. Where Q is a constant rotation matrix and it does not depend on time. This means that we are reorienting the body coordinate axis, but the body itself is unchanged, right? This we already talked about. So after this, if you compute the differentiate the rotation matrix into r dot q, now you can compute this thing r dot transpose r transpose, which would be r dot q transpose r transpose. From here you'll eventually arrive at r transpose. So it is just a matter of like q transpose, you solve it and you will get r dot r transpose. Why? Because this quantity would be identity matrix. So from here we can say that r dot okay, for this different frame we have the same r dot r transpose relation. So changing the orientation of the body coordinate system does not change r dot r transpose. Therefore space fixed Angular velocity is independent in the body frame orientation. Okay, the other option was it is independent of the choice of the orientation of the fixed coordinate system. It is independent of so if it is independent of the choice of orientation of the fixed coordinate system, this is wrong, because suppose we want to rotate by some constant rotation s, and if you would differentiate and do everything, you see that the components would change. This is not independent of fixed frame orientation, it rotates accordingly. Okay, the other option is it is dependent on the origin of fixed coordinate system. Angular velocity describes rotation, right? Rotation is independent of translation. Changing origin of the fixed frame only changes the position vector and does not change the rotation rate. So angular velocity does not depend on the origin. The fourth option is it depends on the origin of the body coordinates. Again, angular velocity is rotational motion and it is independent of where you place the origin. So translation does not affect the angular velocity, all right? So yeah, don't think. One thing is that you should not think angular velocity is intrinsic and frame free, but its component depend on the frame which is in which it is expressed. Okay. The propagation of linear and angular velocities can be used to obtain the linear and angular velocities of links in a serial robot with rotary or prismatic joint. Is from the fixed coordinate system 0 to the free end n in a serial robot is from the fixed pace to the moving platform in a parallel robot. It can be used in parallel robot with multi degree of freedom joints. Multi DOF I am writing. Okay. Okay. So what does the questions that we'll be answering here are what really velocity propagation means, where it is valid, and why it works for serial chains, why it does not directly work for parallel robots. Okay, so the propagation of linear and angular velocities, we already saw this, right? And so let's look at the options. So what is velocity propagation in the first step? So each link is connected to the previous link, right? And we derived the angular velocity propagation, and we use this formula, right? Omega I minus 1 plus z I hat into theta I dot. For prismatic joint, it is just omega I is equal to omega I minus 1. Okay, so then we saw what is linear velocity propagation for prismatic joint, etc., and what is recursive velocity propagation. All of these are in terms of cross products and everything. So why does it work? Because the serial manipulator is a chain and each link has one predecessor. So velocities do propagate uniquely from base to the tip, and there are no loop constraints. Okay. So if we look at the first option, it can be used to obtain linear and angular velocities of the links in a serial robot with a rotary or prismatic joint. So this is exactly what propagation equations do, right? We derive these equations specifically for R and P joints, and the statement is true. It is from the sorry, it is from fixed coordinate system 0 to the end vector n of the serial robot. Velocity propagation starts from omega 0 equal to 0 and v0 equal to 0, and then recursively we find omega 1 v1, omega 2 v2, omega n vn. So propagation goes forward from base to tip, and this option is absolutely true. Okay. It is from fixed base to the moving platform in a parallel robot. This is wrong because parallel robots have closed loops. Velocity cannot be obtained by simple forward propagation, right? You must use loop closure constraints, constraint differentiation, elimination of passive joint rates, and then there is no single chain from base to platform. The simple propagation does not work. Therefore, option 3 is definitely incorrect. And option 4 is it can be used in parallel robot with multi-degree of freedom joints. So it's incorrect because parallel robots have multiple branches, closed kinematic scopes, and passive joints. Velocity propagation does assume open chain and unique predecessor, which means that one link should be only attached to one link before it. So you cannot propagate directly because velocities must satisfy the loop constraints. So, velocity propagation relies on open kinematic chain, unique parent link, and no loop constraints. Parallel robots do violate the condition, and they also require k theta dot k star phi dot is equal to 0 wala equation. It is a completely different framework. Okay. So base to end, it moves from base to end, but it must work for parallel robots is wrong, and the closed loops actually in the parallel robots break propagation. Okay, so final options are these two. Okay. I'm just taking one question, but I won't be writing it. I will just be speaking it out here, and then, or wait, it won't take much time. This is the last question that we are taking for today. The Jacobian matrix for a spatial manipulator moving in 3D space cannot be obtained by differentiation of a vector valued function, okay, is not a proper matrix as elements have different units, does not have well defined determinant, and the fourth option is cannot be inverted always. Okay. So again, this is a very conceptual question, and you should understand Jacobian here. So what happens if we have spatial Jacobian and there is dimensional inconsistency, or so all of these. So let's talk about it. So you know what is a Jacobian, right? You have understood it properly. So what is a proper Jacobian? All of the components of these x should have proper inverse. What is x? Just let me write it because it would be very problematic if I don't write. So what do we know? X is equal to, let's say there is some function of theta, okay, where x belongs to Rm and theta belongs to Rn. Okay, so the Jacobian is del psi by del theta. And each column for this is del x upon del theta I. This is an example of proper Jacobian. Okay, so all components of x have the same physical units. What is a manipulator Jacobian? In this, we don't do this, it is different. We define linear velocity and angular velocity. So, A is equal to j theta into theta rod. That is the whole concept J. Okay. This is not derived by differentiating a 6 cross 1 vector function x, y, z, alpha, beta, gamma, y, because angular velocity is not the time derivative of the orientation parameters. It is not alpha dot, beta dot, gamma dot. Instead, omega is extracted from r dot r transpose. Thus, a spatial manipulator Jacobian is constructed from velocity propagation, cross products, angular velocity relations, and it is not obtained from direct differentiation of x, y, z or the orientation parameters. Okay. That is why here option 1 is true. It cannot be obtained by differentiation of a vector valued function. Okay. Then the top three rows of the spatial Jacobian are linear velocity components, which have the unit of meters, and the bottom three rows are angular velocity components. The units are radians. So Jacobian has mixed units, length in the first three rows, and it is unitless in the last three rows. Thus, it is not dimensionally homogeneous. Therefore, many matrix operations like condition number becomes meaningless unless scaled. Hence, option 2, which is it is not a proper matrix as elements have different units, is correct. Okay. Does it have a determinant? Okay. For let's say the determinant exists, so statement does not have well-defined determinant is false, because determinant exists for a square Jacobian. It is meaningful for singularity detection. Thus, option 3 is not correct. And then it cannot be inverted always. It can be inverted if the determinant of j is not equal to 0. It can be inverted, so it can be inverted sometimes. The statement cannot be inverted always is wrong. It is technically true in trivial sense, but our logic is this is not a defining property of spatial Jacobian. Even true Jacobians cannot be inverted always. Singularities can occur, so this is not a special property. Therefore, option 4 is not correct. Okay, so angular velocity is not equal to alpha dot, beta dot, gamma dot. That was important. And the spatial manipulator Jacobian is not the mathematical Jacobian of a vector valued function. It is constructed using this concept in robotics. And then yeah, dimension you have to take care of, and thinking determinant does not exist because matrix is non-homogeneous is wrong, because determinant is purely algebraic. And then thinking cannot be inverted always must be incorrect because of singularity, but singularity exists even for proper Jacobian, so not a defining feature. All right. Okay, so I think we are done with today's lecture. If you have any doubts, you can ask me. Else we'll close the session. Is there something that you want to ask? Please unmute yourself if you want to ask, or because I don't have the access to chat box right now. Okay, I think we are done. Okay, so thank you so much for attending today's lecture, and we'll meet at the same time from 6 p.m. to 8 p.m. on next Monday. Thank you. Bye.
Thank you, ma'am.
Yeah, sure.